So just a quick review of where we are. We're actually at the surface contact. Alright, so we will be discussing all about these things in hopefully in this video, I guess. I don't know. So let's just start off with the thing. Alright, so the surface contact itself, alright, it's kind of deal with yielding and the yield stress. Okay, so I believe you know what is yield stress. Alright, so for example, you have a certain stress strain curve. This is strain, this is stress. So if you were to pull, this is the elastic limit, right? Linear. Alright, this means that you will not deform. Up to a certain point, there will be something called the yield strength. Alright, so after you exceed the yield strength, the things start to deform, and this is the deform curve, which is somewhat non-linear. Sometimes it's linear, depends on the material. So this is the explanation of the yield strength, alright, Uy, which at this point. Alright, so is the true elastic limit, or is where this is the true elastic, or this is where the limit, where this is the last point of elasticity. After that, once you reach this point, alright, then you will go on to deformations. Alright, or true, and nonetheless true elastic is called a proportionality, so therefore it's also called a proportionality limit or elastic limit. Alright, or the yield strength or the yield point. So these are the different names they call it. Alright, so I hope that you kind of get it clear. And therefore this graph over here shows you the yield strength, how the yield strength is being determined by the material. Alright, because sometimes we know that the yield strength of the material is this one, right, this elastic region. Alright, but however, because realistic case, when you do some testing, or it's very hard to actually determine where is the point where it's yielding. So I think they are looking at this point to this point, 1 to 3, and then 3 to 4. Alright, these 2 points. So they take a look on when it start to deform, and when it start to deform, alright, and then if you were to release the material, alright, this thing over here will be the elastic region again. But this elastic region is parallel to this Hooke's law region, right? This elastic region also. So therefore, using this thing over here, you can predict where is the point where it starts to yield. Alright, so it's somewhat like a 0.2% offset method. So this is the strain. Alright, so there will be a 0.2% strain. Once you reach this 0.2% strain, alright, and then you release, alright, and then you see what are the stuff that what is the difference between them. Alright, you look at the curve and things like that. Like, so in other words, this graph is showing you what is the method of determining the yield stress. Alright, what do you do to conduct the yield stress, to find the yield stress. Alright, yeah, I think you get what I mean. What do you do to conduct the experiment to get the yield stress? Yeah. So note of this is the general curve for non-ferrous alloys. Alright, so this type. Alright, so next is that how does the yielding affect the fracture or something like that. Alright, so previously the graph that I've drawn, it's over here. This is the yield strength. Alright, so once you reach a certain point, it cannot take in anymore, you'll fracture or eventually fail. Alright, and therefore this is what it's trying to say. So I will believe these little circles over here are atoms. Alright, atoms. So when you pull these atoms apart, alright, then it kind of break, alright, because there will be a crack in between, right? So this is this form. This is the where it's talking about. Alright, so you are trying to pull it apart in this manner. So this is opening up. Or nonetheless, you will have a shearing where you can shear in this manner. Alright, or you shear in this manner, or you may shear in this manner. Yeah, I think you get what I mean. Alright, so yeah, take note of the words like in plane shear, out of plane shear. Alright, so these are the 2 keywords that you can search. So let me see. So I found this picture which I believe is better, alright, because of the clarity in there. So there is mode 1, mode 2 and mode 3. The mode 1 is what we have said just now. The mode 2 is when you pull in this. So the plane is actually this plane. So you in plane you shear. Alright, so this one is anti-plane. So you are this plane over here, but is trying to slice this plane apart. Alright, so hopefully you are clear. Yeah. Do take note of all these terms because these are the common terms being used for certain materials, not just composite or whatever. Alright, take note of the atoms, how they actually. I think once you know these things, I think automatically atomically, alright, atomically you know what is next. Alright. So this one over here is talking about the same thing as this graph. Alright, the 0.2% offset method. Alright. So for plasticity, alright, if you were to move from A to B, alright, and then you kind of continue to pull it, alright, you over here this region is the permanent deformations. Alright, and up to here already, when you release, alright, you will go back to this part. Alright, and this part over here will be the new elastic region. Okay, this is what it's trying to say for this whole page. In other words, when you pull, alright, and then you pull more, you will come here. And then when you start to release, you release in this region. Or you will not come back to this point. Okay, so this is what it's trying to say. And this is called the elastic perfectly plastic idealization of plastic deformation. Alright, so it's more on the plastic deformation. So this is the plasticity theorem. Alright, so take note of this theorem. Okay, I don't think it's needed, but in the future you may need it. And I think I'll just stop here in case it kind of heavy you up a little. So I think all in all, the takeaway from this few slides is the type of sharing and plasticity concept lah. Right, so yeah lor.